This lesson will show how to solve a non-standard minimum problem. Only standard minimum problems can be solved using duality. Because the last two inequalities among the constraints are of the less than or equal non-negative number type, these are not standard inequalities. Every simplex problem, when solved, must be converted to a maximum problem. In this case, since we're not using duality, we're going to take the following approach. We're going to let z equal negative w. For example, if w is the set of numbers 9, 5, 3, and 6, then z, being the negative of w, will be the numbers negative 9, negative 5, negative 3, and negative 6. What's the maximum value of z? It's equal to a negative 3. What's the minimum value of w? The minimum w is a positive 3. Note that the minimum w is the negative of the maximum z. So if we maximize z and then take the negative of that value, we will get the minimum w. Since z equals negative w, z will be equal to a negative 3y1 minus 6y2. That's because w is a positive 3y1 plus 6y2. So here is the maximum problem that we're going to be solving. We therefore are going to use the approach that was discussed in the previous lesson on solving non-standard maximum problems. This is a non-standard maximum problem. We convert the first inequality to an equation by including a surplus variable, and the second two inequalities we convert to equations by adding slack variables. Notice that since z is equal to a negative 3y1 minus 6y2, when we transpose the y's over to the left-hand side of the equation now reads 3y1 plus 6y2 plus z equals 0. Here is the initial simplex table for this problem. Again, remember that y1, y2, s1, s2, and s3 all must be greater than or equal to 0. Although the bottom row contains no negative numbers in the y1, y2, s1, s2, and s3 columns, we are not done. Reading the solution from this matrix, we see that y1 is 0, y2 is 0, and s1 is a negative 3. Therefore, phase 1 will be needed. Recall that the first row is the pivot row in phase 1 because the first row is responsible for S1 equaling a negative 3. And then applying the ratios, we see that if we go to the first column of the first row, we get the positive ratio 3 divided by 1. So that number 1 is the pivot. Here's the result of pivoting. Reading this matrix, we get y1 is 3, y2 is 0, s1 is 0, s2 is 5, s3 is negative 1. Since s3 is negative, we're going to be pivoting on a number in the third row. Looking at the first positive ratio that we will get, it's in fact the only positive ratio, namely negative 1 divided by the negative 1 in the y2 column. The negative 1 in the y2 column from the third row is the pivot. Now reading the solution, we get y1 is 2, y2 is 1, s1 is 0, s2 is 3, and s3 is 0. All the y's and s's are greater than or equal to 0. We are now in phase 2, but because all the numbers on the bottom in the y1, y2, s1, s2, and s3 columns are non-negative, we're done. Phase 2 is not needed. We don't have to do any further pivoting. We've reached the solution for the maximum z. The maximum z equals a negative 12. The solution to the minimum problem is therefore the minimum w equals 12. Remember that the minimum w is the negative of the maximum z. This occurs when y1 equals 2 and y2 equals 1.